And today we're going to talk about linear versus nonlinear functions. So take out your lesson worksheet if you have a copy. Looks like this. If you don't have a copy, that's okay. You can follow along with me anyway. Here's the problem. Determine whether each of the given functions is linear or nonlinear. Explain each answer. Okay, first of all, we're going to start with a few definitions. So linear functions have a constant rate of change. Now, a constant rate of change means it's the same thing happening over and over and over again. So if you're saving money in a bank account and you save $50 every single week, that would be a constant rate of change. It would always be plus 50, plus 50, plus 50. If you save $50 one week and then 25 the next week and then 75 the next week, that's a variable rate of change, right? That's not constant. So that would be nonlinear, okay? So when they're talking about a variable rate of change, that just means it's not the same thing over and over and over again. Now, we're going to check and see if these relationships here are linear or nonlinear. All right, when we have a table of values, remember we just figure out what the rate of change is, and that is change in y over change in x. So I'm going to look on my table and I'm going to see what's going on here. From 1 to 16, that would be a plus 15 on that side. And then from over here, from -3 to 0 would be a plus 3. So my change in y over my change in x is going to be 15 over 3, and that equals 5. All right, let's try the next one. I'll be colorful. From 16 to 26, that's a plus 10. And over on this side, from 0 to 2, that's a plus 2. So you might look at this and think, oh, this isn't linear because this is different. However, be careful. You got to check your change in y over your change in x. And if we do 10 over 2, that is 5, right? So it's the same thing, same rate of change. All right, then we can check our next one. From 26 to 41, so that's a plus 15 again. Well, since this is a plus 15, this better be a plus 3 over here or it's not going to work. Fortunately, 2 plus 3 does give us 5. So we've got 15 over 3. And again, that is positive 5. So these all have the same rate of change, right? We've got a rate of change of 5 every single time. And you have to make sure you check the whole table, because the first two might work and then maybe the third one doesn't. And then that means it's not a constant rate of change. So this is going to be a linear function right here. And that's because it's got the same constant rate of change. All right, then we're going to look on a graph. Now on a graph, the way that we're going to know that a function is linear is it's going to be a straight line, right? The line is straight. And you have to be careful with this. It means one continuous straight line. It doesn't mean a straight line going up and then a straight line going down, right? No zigzags, okay? No curves, no zigzags. So this one is going to be nonlinear. Whoops. And the reason that this is nonlinear is because the line is going up and then it's coming down, right? So this is nonlinear. So be careful. Even though it's made up of two straight line segments, that does not mean it's linear. It's got to be one continuous line. And another way we can think of it as this line is going up here, right? So this would have a positive slope and then it's coming down. So this is going to be a negative slope. So if something has a positive slope and then a negative slope, that's not the same rate of change. All right, then we've got an equation. So when you have an equation, all you're doing is you are looking at whatever exponent is on the x, right? So we're going to look at the variable x. We're looking at this x right here. And we're going to look at what exponent is on the x. And we want it to have an exponent of 1. Now, we know that whenever we have a plain variable, when I have a plain old x here, that really means x to the first power, right? We just don't bother to write it. So because this is a plain x or an x to the first power, that means this is linear. And that's it, right? If we were to graph this line, we would put a point on -9, right? Because that would be our y-intercept. And then we'd be going up 10 and right 1, up 10, right 1, up 10, right 1. So that would be a constant rate of change. All right, let's look at these examples on the bottom. Now, if you're feeling good about this, and you want to try to do these 6 problems on the bottom, why don't you do that? You can stop the video while you do it and then start playing it again, and then we'll go over the answers together. If you're feeling confused and you want to watch me do a few more, I am fine with that as well. All right, here we go. Number 1. So we're going to figure out our change in y over our change in x, and we need to check the whole entire table. So from 8 to 7, we've got a -1. From -4 to -2, we've got a +2. From 7 to 6, we've got a -1. From -2 to 0, we've got a +2. From 6 to 4, we've got a -2 this time. And from 0 to 4, we have a +4. And then from 4 down to 1, we've got a -3 this time. And from 4 to 10, we have a +6. So we need to check all of these change in y over change in x. So I've got -1 over 2, right? -1/2. Same thing again, -1 over 2. Here I've got -2 over +4. Well, -2 over +4, if I reduce that, would be -1/2, so that works. And then here we've got -3 over +6, which again will reduce to -1/2. So when I look at these rates of change, they're all the same, right? They are all -1/2. Even though the numbers in the table were a bit different at times, they all reduce to the same thing. So that means that this is actually linear because it's got the same rate of change. So I'm going to write a little note here that this one is linear. All right, for an equation, remember all you're doing is looking at the exponent that is on the x. Well, here's my x. I say to myself, is that a plain x? It certainly is, right? If this had an exponent on it, it would just be an exponent of 1. So this one is linear. All right, this one. Hopefully we can tell that this graph is not linear, right? Because it does not make a straight line, a continuous straight line. We got a big old curve in here. So this one is non-linear. And my reason for that would be my line is curved. Right? This big curve right here tells me right away that it is not linear. All right, this equation down here, again, I'm looking at my x and I'm checking that exponent. Well, look at this. This one has an exponent of 2. Right? The exponent is 2. So because that has an exponent of 2 and it doesn't have a plain old x or an x to the first power, that means this is non-linear. If we graphed it, it would have a curve. Number 5, got myself a nice straight line here, a continuous straight line. There's no zigzags, there's no curves, there's nothing, right? This is a perfectly straight line. It's continuous. So this is linear for sure. Number 6, we've got another table here. So let's figure out some change in y over change in x. From 2 to 4, we're adding a 2. And from 1 to 2, we're adding 1. So our slope is 2 over 1, or our rate of change is 2 over 1. I'll write it on the side here. 2 over 1 equals 2. Then I'm going to check my next one. I've got a +4 here, and on this side I've got a +1 again. Uh-oh, I think there's a problem, because if we do 4 over 1, that equals 4. Different, right? These are different. They're not the same. One's a 2 and one is a 4. So these are definitely not the same rate of change. So this is going to be non-linear. And the reason is because 2 does not equal 4, right? These are different rates of change. Hopefully that made some sense to you. I think this is a pretty easy lesson, but if you have any questions, please do not hesitate to ask me in class tomorrow or ask your math teacher. I'm sure they will be happy to help you. Have a great day, and I'll see you next time.